Okay, all good. Hi, everybody. Oh, microphone, good. It's always good. So I think that Kenny just showed some interesting stuff, showing the complications of the multiple types of physics that are involved in modeling these kind of situations. Yeah, you can take it from the simplest case when you're thinking about light and you're thinking about a static flow, and you're thinking about having some pathogen that's floating around and looking at that. So we approach this from a slightly different way. They looked at it in Scotland and from the perspective of starting with the biology and working their way up. I haven't done biology for a really long time. About 20 years ago, David and I think Gerhard were in the UK in Oxford when they came to a microprobe conference. And I was there and I was a PhD student at the time. And that was pretty much the end of when I started doing biology. After that, I moved into nuclear engineering and applications of radiation physics and nuclear engineering. So that's where I live most of the time. So that's how I kind of approach this problem. So rather than read all of that, when I was, right at the beginning of the pandemic, I just moved to Canada. I'd just received some funding and I hadn't really started any work yet. I'd flown home to see my kids and my wife who hadn't moved out to meet me yet. And then I got stuck by the lockdowns. Good job I didn't come back to Canada. I'd have been stuck in a lockdown there rather than at home, which would have been horrible. So I was sitting there in the UK thinking about this kind of problem. I saw the stuff that David and his team have been doing here at Columbia, and we were trying to figure out. We started to think about this problem a little bit, and we noticed that the physics is pretty much identical to a contamination problem. Yeah. So in a contamination problem, we think about something like Chernobyl. So you have a nuclear accident and some radioactive stuff goes up in the air and it floats around and it lands someplace. And then the people there are worried about what it's going to do to them. Well, this is pretty much the same kind of problem, is that if you've got a Far-UVC lamp, you've got some virus in a space, in a room, it's floating around with the air, you've got some source of light. The only real difference is that the light isn't coming from the radioactive stuff, it's coming from the lamp. So it only requires a small change in the physics to get the outcomes that we want to see. So if we start thinking about all these different aspects, the complexity, we can think about the fully mixed solution, we can think about how far away we are from the lamp, we can think about shadowing, we can think about air movement, and all these things, they all play a role in the physics. And fundamentally, there is some nice physics that explains all of this. We can use the Boltzmann transport equation, nice sort of math up there. And we can use CFD using large eddy simulations and Navier-Stokes equations. And we can put some equations to describe survival of the pathogen and the inactivation by UVC. So we take our domain, our room, our space, whatever we want to model, and we do a finite element simulation across that space, across that domain, depending on the discretization that we want to use. We put a discretization on the light source itself. Rather than using Monte Carlo, which simulates particles, we used what we call a discrete ordinates method. This is pretty common in radiation transport for looking at a solution everywhere. And that's quite important, I think, in this space for this kind of work. We released aerosol particles at different points in the grid, load of boundary conditions, and then we were able to initialize a sample at unity, some virus, some concentration of virus, and then watch as it dissipated and changed. So we first started doing this. The first paper that we did came out in 2020. We actually got it done by the summer, but it took months to get out into the world. It was a simple 2D situation. Well, I say simple. We had a light source in the top right corner. We had some inlets and outlets, and we had the CFD. And what we see here is we see a patient. Where's the light? Is that the light? There's the light. So we have a person laying on a bed, breathing out. Yeah, just breathing out one breath. And then we see how over time this circulates around the room. Yeah, depending on where the inlets and the outlets are. Yeah, and this then starts mixing things around. But we see that there is not perfect mixing. There is concentrations in different locations. And we think that's an important point. So we looked at this and we saw that by a static flow, we got a certain concentration as a certain decrease over time with a good airflow or with UV, far UV, whoops, wrong way, wrong way. Here we see a far UVC illumination only, or a good airflow, 8 air changes per hour situation. And then the bottom one we see the case of the coupled CFD, sorry, the coupled far UV with the airflow. And we see that obviously it's decreasing the time it takes to get rid of the bug. And we can see the kind of orders of magnitude decrease over time. So this was obviously a puff dissipating in air and becoming mixed over time. We then started looking at this in terms of multiple breaths. Yeah, we started thinking about things like that. We started thinking about positioning of people and their infection risk. If you actually kind of look at the release, you see how the virus distribution sort of moves around without far UV C, and then we see it with. So we see lots of difference as it circulates around the room. And we see obviously inactivation rates being high close to the lamp, and then being less so away from the lamp, as you would expect. Nothing rocket science there. Oh, here we go. When we looked at the issue of somebody constantly receding the air, so rather than one puff, multiple puffs, someone breathing, we saw similar kinds of behavior in terms of very bad if you've got a low airflow, air removal, better if you have good airflow, and very good if you obviously have the best. And obviously it reaches a plateau. You know, our simulation didn't quite get to the plateau. We ran it for quite a while. Some of these simulations we run on the UK supercomputer over time, the later simulations especially. But what we saw is something like an 85% reduction overall in the room, which we thought was pretty comparable to wearing some kind of N95 mask, depending on how old it was, which we thought was a good result. Importantly, we must be able to capture the lamp characteristics well. So we had some data from Ushio, some earlier data that our model fitted very well. And then we went to started working with the Columbia group a little bit. They sent us some data of their chamber, the one that Kenny was just showing, and we started modeling that up. And we found some interesting things as we did there. We saw that there's obviously a non-uniform far UVC intensity through the space, which obviously has an impact. We also found that drag forces on the edge of the chamber, how laminar the chamber flow was, they all had an impact on the amount of illumination that the virus in the air was getting. So all of these things had an impact. And the upshot of this is that we're able to do similar kind of plots, and we're able to find that the susceptibilities that were previously seen and used didn't look like they were the right ones for the situation under consideration. So we thought that was quite an important result, and we got a paper out of that in 2021. Following on from that, you start looking at bigger spaces. We started investigating some workshops. Actually, I think this was in South Wales, a company in South Wales, and the team at Queen Mary's in London, they started modeling this and seeing how, depending on where you put the lamps, depending on where you were in that space, because of all the obstructions, had quite a significant bearing on the reduction and potential infection risk. And we did similar things in kind of meeting rooms, challenging that fully mixed approximation that is often considered. So we saw quite a lot of difference in terms of perturbations, in terms of sterilizing outcome from a given far UVC lamp installation. And obviously that's a problem if you're going to go and put these out into the world in a large deployment situation. Now, I've said that some of those simulations are quite challenging in terms of computational resource that's required. So it becomes kind of onerous to kind of do this kind of work. So, in a practical sense, you could overcompensate by using more lamps, for instance, and that, or in certain scenarios where you have lots of people in a room and lots of heat generation, as in the very first talk today that was given, was talking about how that mixing could happen. And it's probably fine, but in other scenarios, it's not. So it's very situation specific. And that may or may not be important in terms of deployment, depending on how you frame limits and the confidence levels that you need in the installation. If you're only using it as a nice to have, it's not that important. If you're using it to provide a given degree of protection, that's a different outcome. But rather than do huge numbers of simulations many times, what you could do is do a smaller subset and then apply reduced order methods or machine learning to this kind of problem to give you, some kind of basis function that you could apply in a more simplistic model. Now, we started looking, whilst other groups were looking at the pathogen in large chamber situation, coming from the nuclear background, we had a slightly different thinking. We were more interested actually in reliability of our code and trying to figure out the real world situations and how you might be able to do dosimetry in air in those situations. I was going to present something that isn't quite ready yet, so I'm not going to, but we got to the point where we did some early stage work where we think we might have a surrogate that we could use in the field for some assessment. Now, you might see that we haven't really published, our team hasn't really published anything since that 2021, 2022, early 22 point. And that's because the group in the UK that I was working with, especially at the Cranfield University site, they didn't get any funding for this work and they moved on. And with that, they took their CFD solver with them. I mentioned at the beginning that when I came to Canada, I was taken on to do a particular task, or one of my tasks, and that was to develop a health physics and environmental impact code for the nuclear sector to make better predictions of risk to people, especially in this small modular reactor era that we may be in. So we started developing a code in early 2020 that wasn't ready to go. It's just about ready to go now. Yeah. So we now have on the Canadian side a similar code that uses discrete ordinates that can do the CFD in 3 dimensions, and the code is called Caribou, and it will be open sourced. Yeah, probably not for about 12 months, but we will, depending on the development level, we will open source this code for the community to be able to play with. People have asked, how would you be able to use this? Yeah, well, if you take a space, you've got a CFD model, you can run it through a mesher. There's lots of meshing software that's available now. Some given boundary conditions, you can do the simulation and you'll be able to get an outcome. So we have this is ready to go with the Far-UVC now. Just need some more testing and some more applications to run it on. And maybe one of those applications is the Leeds chamber. Go a different way to what Kenny was just saying, and maybe that would be an interesting way to approach this. But that's one for later conversation. Anyhow, so we get to the end of it. So we obviously know it's a viable technique for reducing transmission of pathogens in air. We know that is good for that. We now know that high fidelity codes, they can model controlled experiments very well in the lab. So we've done that, validated the code, which we thought was a good thing to do. Very common in the nuclear space, so why not project it here? We think that we've got better estimates of susceptibility. More experiments need doing. We need to test our code against them, to make sure that it's doing the right things. Obviously, we know that high fidelity modeling can help inform placement, but more validation and verification is clearly going to be required. And now that the approaches to modeling is pretty straightforward, I want to say trivial, but the way to do it is understood. So it's more a question of adding more physics to it and using a Moose-based simulation tool like my Caribou code. For those of you that don't know, Moose is a framework that comes out of Idaho National Lab. You can do all kind of physics with it. It's really good. So we've developed that. Should be able to help with that. And that's more or less it. So we've got a team of people involved. Me, Andrew Buchan from Queen Mary's in London, and Liang Yang from Cranfield, the Columbia team providing the data, and my group in Canada is just a couple of us right now. If funding comes our way, we'll do more. So there you go.
We have time for one question. Do you mind if I stop here just for a second? It's easier.
So do I.
Thank you for that. I always wonder how much putting stuff in the room makes a difference. Putting furniture and stuff like that would make a difference to the flows of the particles.
And it clearly does. So, you know, even in our earliest simulations, we saw how that flow changes quite substantially. So obstructions are quite important and need quite some investigation. But one of the things that is always necessary, because I can throw anything in the computer, yeah, you need the validation cases to put it against. Without validation, it's worth nothing. Yeah, so you really do need good dosimetry, good ways of quantifying the flows, you know, and anything and everything else to build certainty and confidence in these, so that you can apply them in practice.
We have time for one more. Okay, well, I have too many questions to make it. So I'll try to simplify it. So you said this is a coupled simulation.
Yeah.
So are you using a separation of variables to solve this, or is it a fully coupled?
It's a fully coupled simulation that employs the Moose framework. So if you type in Moose framework into the Google, you'll come up with Idaho National Labs work. They do a great piece of work because nuclear reactor physics is a fully coupled situation. So we're borrowing the same kind of approaches to do the modeling. So in terms of the radiation transport, the fluids, and the virus, but potentially we could extend it to chemistry and everything else too, in a coupled manner.
So is your code, does it interact with OpenFOAM or what?
So depends on which one. The Cranfield guy that worked on the original work, that was his in-house code, a Cranfield in-house code, which is why it kind of stalled us doing more work. And my code, based in Canada, is based on the Moose framework using their intrinsic fluids capabilities.
This is a good conversation over happy hour.
Over
All right, thank you so much.
No problem.